Okay, we have looked at perceptual learning algorithm in part 3, and as we said, there is actually a theoretical result that shows it has to converge if the data is separable. Okay, so this is something we need to do now. We need to first define what do I mean by separable, right? What is the exact mathematical definition of linear separability? And then we need to state the convergence theorem, and finally look at a proof. And the proof is actually very simple if we do it in a geometric way. Okay. Now, first, what really do I mean if I say that a dataset D is separable? Well, I mean that a dataset D is said to be linearly separable if there exists some unit oracle vector. Well, what is unit oracle vector? Let's do it step by step. First of all, it's a unit vector. That means its norm is 1, its length is 1. Okay. And secondly, it's an oracle vector. What does that mean? That means it's a perfect vector for this data set. This vector U can correctly classify every single example X and Y pair in this data set D, not just correctly, but also with a margin at least delta. That means I have a safety net, I have a safety zone of delta, right? So I just need to be positive in order to correctly classify it. But I'm not just barely positive, I'm positive by at least a margin of, let's say, 1, okay? So you just need to be greater than 0 to be considered correctly classified. But what if I'm greater than at least 1? Okay, then between 0 and 1 is my kind of safety buffer, okay? So this concept of margin, of delta, is actually central to machine learning. And we'll see a lot of margins in this week, but we will see more in SVM. All SVM does is to optimize this margin. Okay, optimal margin classifier. That's the original title of the SVM paper. It's called optimal margin perceptron. Okay, perceptron itself does not optimize this margin. Perceptron is perfectly happy if it can classify every single data point, every single example in the training set correctly. As long as that is achieved, there presumably are multiple ways to achieve that. Perceptron doesn't care. As long as I'm correct on every single example, I'm fine. Do I need to optimize the margin? No. That's why perceptron itself, in a vanilla way, is not as good as SVM. But next week we'll see how to make perceptron, kind of optimize margin. Not optimal margin, but large margin perceptron. That's what makes perceptron actually useful in practice. Okay. So how do I define that? This oracle vector. Well, I mean that the classification result, that is the dot product, is at least delta. Okay, so if this X is a positive example, then Y is positive, and then both the dot product and Y are positive. And if it's negative example, that is Y is -1, and the dot product also needs to be negative. But anyways, the value of that dot product needs to be at least delta for every single example. Okay, then we can call it a margin of at least delta. If the data set is linearly separable, then we have this convergence theorem that the perceptron can be shown to converge to some linear separator. Okay, not necessarily the same oracle vector. That is, as I said, perceptron must converge to a particular linear separator, but not as we don't know its margin. And this convergence must happen after a finite number of mistakes or updates. And how many updates? At most r squared over delta squared updates or mistakes, because we know that whenever there is a mistake, there is an update. So there are equal number of mistakes and updates. Okay. What is this r? This r is called the radius of the data set. It's basically the longest length of any training example. Okay. Or in other words, the maximum of the norm of training examples. Doesn't matter if it's positive or negative. Okay. And we'll see what that means in a minute. But right now, let's look at this form of r squared over delta squared. And we see that this form is independent of many factors. It's independent of the dimensionality. That is, whether this x or this u is n-dimensional vector or 100-dimensional vector or 10 million dimensional vector, doesn't matter at all. Okay, and it doesn't matter in the data set size. If you have 1 million examples versus you have 10,000 examples, it's the same. This convergence rate or convergence bound does not care. Okay, and it's order independent. So you have, let's say, 1,000 examples in D. If you shuffle them, you got the same convergence bound. But actually, the actual order matters in output because perceptron actually is sensitive to the order. Okay, but the worst case number of mistakes is not sensitive to the bound. Okay, there are a lot of things that perceptron is in practice sensitive to. For example, the order of examples, but the worst case behavior is not sensitive. Okay, and as long as this is linearly separable, you have to converge. Okay, and that is independent of order as well. Okay, but this bound does scale or is dependent of the difficulty of the problem. In other words, the difficulty of the problem is really related to this delta, this margin. Because intuitively speaking, if you have a larger margin, that is, the positive and negatives are far apart, so they're easy to separate. And if they're very close to each other, then the delta will be very small. And you can see that the bound will be bigger. That means you will likely make more mistakes before you can converge, right? So we'll look at that in more detail. But for now, let's prove it. And this proof was from 1962, 3 years after perceptron was invented. And it's remarkable. A lot of machine learning proofs were based on this proof, or kind of variations of this on the same theme, right? So this proof is in 2 parts, and we'll explain both parts in terms of geometry, right? So assume the initial weight vector is 0, okay? Actually, this proof would work if you change a little bit, even if the start weight vector is not 0. Okay, that's part of your exercise that you need to prove that even if it's not non-zero, you can still prove convergence. Okay, and let's assume W superscript I. Okay, W of I is the weight before the ith update on this particular example xy. Okay, so because it's the ith example, we cannot write it as a subscript, because a subscript would mean like it's the ith dimension. So we'd rather write it as a superscript. Okay, so the update on the ith example, ith update on xy looks like this, right? It's very simple. Wi plus 1, that is the weight vector after ith update, was the weight vector before the ith update plus y times x. Okay, if it's positive, just plus x, let's say. And let's assume y is a positive for now, okay, to simplify the proof. Okay, because we just use a positive example to demonstrate that, right? Now, let's say these are the deltas, right? So every positive example must be at least delta away from the separating hyperplane, from the decision boundary. And that is, if we assume it's linearly separable by this unit weight vector, unit oracle vector u. Okay, so let's assume this distance is 1, this length is 1. And because u is pointing to the right, it means that if an example is to the right of the origin, it's classified as positive. And if it's to the left of the origin, it's considered negative. And all the positive examples are at least delta away from this decision boundary to the right. And all the negative examples are at least delta away to the left. So there's nothing in between these 2 blue dotted lines. So that's the idea of the margin, right? The safety net, the safety buffer, okay? There's nothing in this kind of buffer zone, okay? Everything is outside of these 2 lines, okay? Now, let's say you're trying to correct or update on this example x, right? So your current weight vector is wi before this update, which incorrectly classified this example as negative, right? Because the dot product will be negative. See, x and w do not align very well. They have negative alignment or negative dot product. And how do I fix it? Well, I add it to the current weight vector, and the new weight vector, or wi plus 1, will be this one, this direction, right? Because wi plus x is wi plus 1. Okay. So now what can I infer about wi plus 1? Well, I can say that it's more likely to be aligning better with the oracle vector. That is the correct direction. Because we know the correct direction is to the right, right? So at least after this update, I can prove that it's aligning better with the correct direction. How do I say that more mathematically, more formally? Well, because I know that x is to the right of this delta margin, right? So in other words, the projection, if you project it to the u direction, to the correct direction, oracle direction, the projection is at least delta because it's outside of this safety net, right? Safety buffer. So this projection is at least delta, and this is, if you move it here, this projection is at least delta, right? And so this projection, that is the the weight vector I, the current weight vector, if you project it to the oracle direction, that's the u dot product w of I. And because u is a unit weight vector, so the projections are indeed the dot product. If u is not a unit, then you cannot say that. You have to kind of scale it by divided by the length or the norm of u. But because u is a unit vector, that means it's less 1. Everything is a lot simpler, right? So the projection of wi along the correct direction plus the projection of x on the correct direction is the projection of wi plus 1, the new weight vector, along the correct direction. In other words, we prove that the new weight vector wi plus 1 must have longer projection along the correct direction. In other words, it aligns better. It has more agreement with the correct direction. And how much better? Well, at least delta, right? Because every positive example is at least delta away from the separating hyperplane, right? So that's very nice, right? Because if you prove by induction, then you can say, you show that the projection of the I plus 1 weight vector wi plus 1 must be at least I delta. Okay, it must be at least I delta, right? Because if you add another example, add another update, you'll be aligning with the correct direction even better, right? Every single update gives you at least delta additional alignment with the correct direction. So you're making progress, you're making steady progress along the correct direction, right? So, and because of that, you can show that the norm or the length of weight vector after I's update is at least L delta, because even the projection along the correct direction is L delta, then the length itself must be longer than L delta, right? So that's the geometric version of the proof. Now we also have to understand the purely algebraic version of the proof, which we can just translate what we just said about geometry back to the equations, back to the boring part of mathematics, okay? So wi plus 1 is wi plus yx, that's the update. And if you just dot product both sides, left and right sides, with the unit oracle vector u, and you got u dot product, this is u dot product, the old one, plus y times u dot product, the current example x. And because that is at least delta according to the separability condition, right? That's the minimum margin. And we can show that, you know, the u times the new vector is at least the u times o vector plus delta, which is what we said here in geometry. That is the alignment with the current, with the correct direction is at least bigger by delta. So that's the amount of progress you can track on the correct direction. So by induction, you have at least I delta, I times delta alignment with the correct direction after I updates. And then you can do some little math, and then you can show that the length of the I plus 1 vector must be at least L delta as well. And to explain it in geometry is easier, because if you say the projection is at least delta, then the length itself is even longer, right? Because the projection of a vector is always shorter than, actually no longer than the vector itself. So if the projection is at least I delta, then the length is of course even longer, so at least L delta as well. Okay, so this is the first part. That's kind of the progress or alignment on the correct or oracle direction or projection. and then we showed a lower bound of the length of the weighted vector after I updates. Now, in part 2, we showed the reverse direction, that is upper bound. And if we have both lower bound and upper bound, then we can kind of bound something in between, that is the maximum possible value of I, that is the maximum number of updates or the maximum number of mistakes. Okay, so part 2 is the upper bound of the norm of the weighted vector. Part 1 was the lower bound. Okay, so again, the updated equation. Now, this part is actually a lot simpler than part 1. Okay, so for positive example x, because this part has nothing to do with delta, nothing to do with margin. This part has only something to do with the radius and the mistake. Okay, now because you made a mistake on x using the current weighted vector, you need to update. So wi plus x equals the new weighted vector wi plus 1. And because you made a mistake, this dot product must be less than 0, actually less than or equal to 0. Okay, so if you just take their norm and if you expand it by Pythagorean, or sorry, generalized Pythagorean theorem, because these guys are not perpendicular to each other. If wi and x are perpendicular to each other, then it's the Pythagorean theorem, or 勾股定理 in Chinese, that the new weight vector's norm must be, the square norm must be the square norm of the old vector plus the x square norm. But because they're not perpendicular to each other, you need to take the dot product in between. So this is very similar to like a plus b squared is a squared plus b squared plus 2 times a times b, right? Except that the times between these two vectors are interpreted as a dot product, which is very natural. So you can just think of these guys as numbers, so it's exactly the same form. So this is called the generalized Pythagorean theorem. And so that means that the square norm of the new weighted vector is the square norm of the old weighted vector plus the square norm of the example plus the dot product. And we already said the dot product must be less than 0. Otherwise, you did not make this mistake. And because you made a mistake, and that's exactly why you're updating on this x, this part, the dot product must be less than 0. Okay. And what about the bound for x norm? Well, it's bounded by r, because we already said r, the radius, is the maximum length, right? So that's the longest or farthest away vector or data point. So it's bounded by r squared. So in other words, you can say that the square norm of the new weighted vector is at most the square norm of the old vector plus r squared. And by induction, it's less than I times r squared. So we achieved a upper bound for the weighted vector as well after I updates. Now we already had from part 1 a lower bound of the norm without a square, by the way, that is I delta. And if we square it, so the square norm of weighted vector after I updates is at least, in the lower bound is at least I squared delta squared, right? And then you can show that I is less than r squared over delta squared. Okay, that's the end of the proof. The number of updates is at most r squared over delta squared. That is radius squared over margin squared. And here's a little kind of demo, or animation showing this two bounds, the lower bound and upper bound. Okay, so first is the upper bound on the square norm. Okay, that's the quadratic upper bound on the square norm, and then it's the lower bound, linear lower bound on the norm without square. And because of that, they must meet somewhere, that's how you can show the I. So if you work out the math between the two, it's actually that this lower bound will increase and the upper bound will also increase, but at a lower speed. Increases slower. Then they must meet somewhere in between. Okay, that's the end of the proof. And convergence bound again is in the worst case r squared over delta squared, and it's independent of many things, right? Dimensionality, number of examples, order of examples, and constant learning rate, right? Because if I change the learning rate to 2, or let's say 200, it doesn't matter at all, right? but it's dependent on the separation difficulty, that is the size of delta, the scale of delta. Okay, so this case is a narrow margin, very small delta, so it's hard to separate. You would probably spend longer time training on this example, training on this data set, versus if it's widely separated, wider margin, considerably easier to separate, and you probably, likely will spend less time training on this data set, right? So that's also kind of modeled by this R square over delta square. And it's also dependent on this initial weight factor W0. Well, what does that mean is that the worst case mistake bound or convergence bound is dependent on the initial weight factor. That is, the initial weight factor changes how fast it converges, but it will not change whether it will converge, right? So as long as the data is separable, regardless of whatever weight factor you start with, you are always going to converge, but your convergence speed might be different. That's what I want to say. In your exercise, you would need to show that perceptron will converge regardless of the choice of initial weight factor, as long as the data is linearly separable, okay? But you probably have a different convergence bound. And also the feature scale that is related to this R. So if some features are very, very big, then your R will be very big. If some features are very small, then your R is very small. So really it's depending on these three things. Okay.